so people missed a little bit because it was taking some time. But basically, things about norms are on the board. These are the properties of a norm. Now we're starting to look at different norms. If people have questions about this, you can ask. The most common type of norm that I think we talk about, and even in our papers we'll say, in our papers a lot of times we write this, that this signifies the Euclidean norm. So that's just using different notation. But what the Euclidean is also known as the 2 norm. So it's a type of one of these p norms that specifically is when you put in x2. So it's equal to the sum from I equals 1 to n, where n is the number of components in this vector x. So you take each component to the second power and then to the 1/2. So that would also be equivalent to essentially the x1 squared plus x2 squared. If you have like the norm of x where, or I guess this is if x is equal to x1, x2, then the norm of x2 is equal to this. So then you can see it's kind of following that sort of distance-like formula. So that's probably why you've seen that one before. It's also good to recognize that this is actually equivalent to, so we can start using some more fancy vector notation. So this is actually the same as x transpose x to the 1/2. It'll probably take a little bit of getting used to start being able to do, to work in more vector notation like this. But I can really quickly just show what this means again. So this would be like, you can tell that this is true because if you take the same thing, x1, x2, this is x transpose because we usually mean x when we say it. We usually mean it's a column vector. So then if you were to take these together, so this is x transpose x is equal to this multiplication, so it's x1 squared plus x2 squared, and then if you do that to the 1/2, you can see that it's this. And then, so of course that would scale to higher dimensional x's, like you could also, then you could imagine like, oh, say it was 3-dimensional, oh, okay, I can see that's exactly the same thing, and stuff like that. There's something called equivalence of norms, which doesn't really mean they're equivalent, so it's kind of weird and confusing. What it means is that, like, you can scale, you can put like upper and lower bounds on one norm based on another norm and multiplied by scalars. So I guess it's sort of saying, so like this is one idea of, so here's the idea of the equivalence of norms. So in Euclidean space R to the n, all p norms are equivalent, but not really. That's why this is such a confusing way that people call this. It doesn't actually mean equivalent. So what it means is that given integers alpha and beta from 1 to infinity, so that'd be like between 1 and infinity, but not beyond. To infinity and beyond. There exists C1, C2, which are positive real numbers such that C1 of x alpha is less than or equal to x beta is less than or equal to this C2 x alpha for all x contained in R to the n. So this would be if you have the p norms. So these would be integers between 1 and infinity. And then so if you essentially if you take one of the norms, then you could find like upper and lower bounds on it with these other ones. So the reason that turns out to be important is that it allows us to talk more generally when we give statements. I'm probably standing in the way of all these people who want to watch this. So in the sense that what we're going to do is in a lot of the following, we're going to say something like, okay, if the norm is like this, then the following. And we won't specify which norm. But part of the reason that we can do that is related to the fact that there's some type of relationship between norms. So if I was to tell you, like, if the norm is less than delta, then the following thing holds or something. And then, well, then you could imagine that if you were in one of the other norms, like, so then if you were, let's say, like, oh, okay, well, I chose the norm. Let me just try to give this idea. So pretend that I have a statement, something like, if the norm of x is less than delta, then da 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 da. So then you could say like, oh, okay, let me try that. I'm going to test that with this beta norm. So if the beta norm is less than delta, then the following thing holds. And then you say like, oh, okay, but I wanted to use the alpha one. Oh, okay, so you said if the norm of x is less than, now probably you have a different delta, but then you could, because they have some relationship between them, there should be a way that if your norm in the beta norm is less than delta, then there should be some other number that the alpha one is less than. So like by making general statements that aren't related to specific numbers on the upper bound, like by just saying things like, if you can find a norm where you have it less than some positive integer or something like that, well, or positive real number, then, well, you could find like a positive real number in multiple norms, and it would just maybe be a different positive real number, but it allows us to get some type of generality that's going to come up in all the following of what we're going to do. That's okay? Okay. Then the next thing, there's actually matrix norms as well. So I think it's good to know that if you see, so these don't come up in our papers as much till now, but research group discovery is just getting started, so who knows what's going to be in the papers in a year. And there's norms for matrices. So say you have a m by n matrix. Oh, I should have said. So the utility of a norm for a vector is essentially some representation of the magnitude of the size of this vector. Because you can imagine that like if every entry in the vector, so say you take a p norm, say you take the 1 norm, or you take the 2 norm, or you take the 3 norm, so you take one of those. In any case, if you have something that's like x to the 1 over p, the sum of all those to the 1 over p or whatever, to the p, and then to the 1 over p, if every entry in that is small, then regardless of which norm you use, that number is always small. If every entry in that is big, then regardless of which norm you used, every entry in that is big. Or every norm of that is big. So it's essentially like a reflection of size, in some sense, of a vector, when otherwise size doesn't really make sense for vectors. So we talk about sort of absolute value turns out to be essentially the one-dimensional vector case of what you get for all of those norms. So then when we look at absolute values, we think of that as meaning size of a number. And then so similarly, if you want to talk about how big is my vector, then you talk about it with a norm. And then, so now is sort of the question of, well, could you talk about how big is my matrix? And it turns out this is useful for a number of different things. But, so then, yes, people have defined a lot of different ways of, again, talking about how big is my matrix in some sense. So these are, again, called norms, but now, so this is an induced, what we call an induced norm for the matrix A. And this is how you happen to define it. So it's the supremum. So I should clarify supremums versus maxes. So supremums don't necessarily get reached. It's like a greatest upper bound. So it's not necessarily meaning that you, yeah, it's like a greatest upper bound. So maybe you never hit that number, for example. Maybe it's like very asymptotic. And so you would say the supremum is whatever number is on this line, even though your function is like not really there, but it's a. So this is the supremum when x is not 0 of the p norm of a times x. So a times x is a vector. And then over the p norm of x, and then it turns out that someone found out this was equivalent to the max for x p norm is 1 of the p norm of ax. So it turns out people have been able to derive a few of these, or a various number of them. And so, for example, you can have a one norm of an induced one norm of the matrix A. This would be the max over J of the sum from I equals 1 to M of Aij. So this is essentially a max column sum. So you sum in your column, you sum all the entries, and then you take the largest of all the sums. So you can see how that kind of represents size of the matrix in some sense, even though it's sort of vague. But I think that's going back to, like, it's not vague, it is exactly what it is mathematically. In our mind, I think, the concept of size of a matrix seems undefined, but when you put a mathematical definition to it, then it is what it is, and you check with that. And then so that's why defining things in mathematics is always so important, because it reduces vagueness. Whereas it is not obvious to see what does it mean to talk about size of a matrix, and if I said that to you, you would have a picture in your mind. But then if you say, this is exactly what I mean, then I say, like, okay, that's what you mean.
This is a mathematical definition. Could be the line as well, right?
It could be, yeah. And then so here's the infinity induced norm, and so this one's a max row sum, which I think is what you're asking.
Yes. Mm-hmm.
So here's another way you could do it. Sum from j equals 1 to m of aij. This is a max row sum. So you take between all the different rows and then you find the maximum. And then you can also have like the induced 2 norm. So that's another one you can have. So it's this idea of the maximum eigenvalue of this matrix that's A transpose A to the 1/2. So so many ways to talk about what's the maximum here. So then so that covers basic concepts and norms. Does anyone have any question?
Is this an M or an N?
Oh, up here? Oh, good question. Over M. So this is related to the M by N matrix. So then this is going, so there are M rows. So then what this one's doing is it's saying like, over here, so here's A, 1, 1, A21 dot 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 AM1, and this one is A12 dot 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 A1N, and then we go down, and this is AMN. So then if you want to sum down the rows, so the first entry, you would go to M. And then if you sum across, oh, what's this one? That one I might have messed up. Then if you sum across the column, I think this one should be N. Good catch. Thanks, Kit. Okay, does that seem good? Okay, cool. So the next thing is getting into a little bit of abstraction on how to define things in sets. So the way which we define sets now. So here are some set definitions. So here is a set S contained in R to the N. Oh, I should just say, I think it's a little, I never thought in terms of sets when I was an undergraduate. But then just imagine like it being like collections of lots of things. So I think we have like an intuitive sense of what a set is, but I never thought in terms of it. So now we're going to start thinking a lot about sets, and having these appear in all our work. So a set S in R to the N is said to be open if for every vector X in this set. So this means X is a member of the set S, is what this notation signifies. One can find an epsilon neighborhood of X. I'll go through this in just a minute. Here's the definition of this epsilon neighborhood. So I'm going to define this. This neighborhood is Z that's contained in R to the N such that the norm of Z minus X is less than epsilon, such that this epsilon neighborhood is contained in the set S. So, or I guess is a subset of. So this means, so this cup means is a subset of. So I guess S in R to the N means S is a subset of R to the N. So that's what this notation signifies. And then X contained in S means that the vector X is a member of the set X, or set S. So we'll clarify what's going on here. So here what's being said is that so intuitively we have a lot of thoughts in our mind about the idea of an open set. For example, when we talk about this one, so like 0 to 1, and probably you've seen that in like a much earlier math class, and they said, oh, that's 0 to 1 open. And then so it's an open set, and then, but so you can define, so we've said that one's open because it doesn't include 0 and 1. And so that's sufficient for like talking about numbers on the real line. But then when we want to get into these larger spaces like r to the n or things like that, we have to define what it means more rigorously. And so we can see how this applies to that example after we explain it. So when we think about openness, that means that, so imagine that I have this set here and that for some reason it's sort of like this weird blob in space. Here's my set S. So if I include this boundary, so here we kind of have an intuitive sense about not including boundaries means open. And that's sort of a way to think about it to help with grasping it. But this is the real mathematical definition that would be checkable in the sense that we're going to use it here. But so if you think about including a boundary versus not including a boundary. So if I start here, and then I try to look at all the z's in r to the n that are within epsilon of my point. So then I say like, oh, okay, so that includes a little bit like all around here. Pretend that is like this. So it has this norm. It doesn't say it's necessarily a 2 norm, so it doesn't have to be like a real circle or anything.
Any kind of norm.
Yeah, any kind of norm. That's one of the p norms, I guess, where they're all equivalent. Equivalent in some way that's not really equivalent. But so say that I take here. So if I have some norm, pretend that my norm gave me this region as being where the norm of the z minus x is less than epsilon. Then I look in this region and I say like, oh, okay, look, over here, it's true that on this side, the neighborhood that I've generated, so here's my whole neighborhood. I made a new set. It's the set of all z's such that this holds true. So it's this whole region inside the circle. Now here on this part of the neighborhood, it's true that the neighborhood is contained in my set S. So that is good. But up here, it's not. So, and that would hold true no matter how small I made the neighborhood around this point because it's on this boundary. So that it's impossible that if I took every z that was within epsilon of that point, that I would continue to get that whole neighborhood being contained within the set. Is that okay? Is that making sense? Should I repeat it?
Can you repeat it?
Sure, no worries. So I'm gonna erase this part right here. So if we take the figure and then say that we're on the boundary. So say for a minute I'm gonna draw a bigger set. Pretend this is really small, but just to show it better. So over here, these points are in the set S. So here's my set S. Here's some neighborhood. If we pretend this is a zoomed in version, that maybe it's really small. So these points are all in the set. So it means this neighborhood is a new set, and these points are within the set S. So I could say like, well, these points are a subset of S, but these ones aren't. These ones are outside that set S. So, and the reason that this is happening is because I'm on the boundary. So even if I make this infinitely tiny small, if I look at all the points in r to the n that are within epsilon of this point, I will always encounter some that fall outside of this set. So therefore, this set is not open. Does that make sense? And then we can see how that is here. Like this one didn't include its boundary. It was open. Now also going to a little bit more, say that I don't include my boundary. And I have the S again. Now it doesn't include the boundary. Now say I'm like infinitely close to my boundary. But because I don't actually include the boundary, I include right up to the boundary. I can always, in some sort of asymptotic sense in your mind, keep going and going and going and always finding infinitely small regions around my point that are still within the set because it never actually includes the boundary. So I'm never on the boundary, so I can't really be outside if I take the epsilon neighborhood around it. So that was open. It didn't include the boundary. That's the same idea with, it's probably easiest to see in the 0 to 1 line, how you can infinitely approach 0 and never get there because it never actually includes 0. Yep. So then, that is, but this is the real mathematical definition we're going to be employing in the rest of what we're going to talk about for what it means for a set to be open. So it doesn't mean I didn't include the boundary. What it means is this. But if you want to try to understand what it is trying to tell you, you can think of some examples where having the boundary or not having the boundary helps it to make sense. Okay. So the next thing we're going to go to is one is a set closed. So a set S is closed if and only if its complement in R to the n is open. So I guess I don't actually have any definition for the complement here, but I can give some example that kind of helps illustrate it. So here is a closed set. It's -1 to 1. The complement is this union, so -infinity to -1. This means union, so set union, 1 to infinity. So those sets are both open. So then the complement is open. So then a set is bounded if there is r greater than 0 such that x is less than or equal to r for all x in S.
You said greater than equal to. You wrote less
Oh.
than equal to.
What's here is right.
Okay.
Sorry. Thank you for the catch. So it's bounded if you can set an upper bound on the norm for every vector in the set. So that would mean like there's no vectors in this set that are like unbounded in some sense. Here we have a definition of a compact set. So a set S is compact if it is closed and bounded.
I think I'll ask the same question as before.
Oh no, that's fine.
Because if a set is closed, it is not at the same time bounded.
If the set is closed. So a set would be closed based on its complement being open.
Right.
So then, and then it's bounded if there is no R such that that's true. Or if there is an R such that that's true. I'm sorry, did I look this up last time or I didn't?
I think we didn't look at this point.
I don't.
I think we thought a compact set is also closed.
So yes, so definitely a compact set
Is closed.
has to meet
Right.
closed and bounded.
Mm-hmm. I think we thought it's redundant to think a closed set is also bounded. So it seems this because the complement should be open.
I do not know this off the top of my head. But maybe you can I think we would have to look on Wikipedia or something. I think there are cases where this could happen because I do not think that, because it turns out, like, if I really look at these definitions, the boundedness and the closedness have very different definitions. Like, one is based on whether the complement is open, and one of them is based on, like, whether there's a bound on the norm. So they're not actually about the same thing. So I think it must be possible to have some mixing and matching in some sense, but I don't know. I don't know. We'll have to look on Wikipedia. Maybe you can take a quick look and then send me what you find, or if you cannot find it, then let me know what you did find.
I think if you have one example, this should be clarified.
Yeah. Maybe if you Google closed unbounded set or bounded open set or something like that, I think if you Google those two, like, essentially you're looking for the counterexamples.
Right.
Yeah, maybe you can send me what you find.
Okay. Complement note.
Then, but that's a really good question, Enrique. I'm just not sure. So, one thing that I think is really fascinating reading this stuff is just recognizing, like, the nature of mathematics and just thinking about how, like, none of this is fixed in stone. Like, the proofs follow from definitions. Like, just as if I told you if a set is closed, a set is compact if it's closed and bounded, then, but if I had a different meaning of closed and a different meaning of bounded, maybe it doesn't hold anymore. And so, like, that really all these definitions in mathematics are here because they're about, like, being able to prove the underlying thing. Like, being able to prove stuff with the definition of closed or with the definition of bounded. But if I was to define those completely differently, then the statements wouldn't hold anymore. I find that's kind of interesting. Like, oh, it's kind of, like, so abstract. You're like, well, math doesn't, like, the definition of closed, like, depends on what I say it is, in some sense. So the closure of a set S denoted by S bar is the union of S and its boundary. So if you have an open set, it's that open set plus its boundary. If it's a closed set, the closed set is equal to its closure. So now we're going to talk about existence and uniqueness of solutions of nonlinear differential equations. So we're going to talk about existence and uniqueness. So what we said before is that we generally take this for granted for the linear systems. And we just say, like, oh, okay, I'm not going to worry about under the conditions under which this holds, because it's actually quite a lot of conditions that you get existence and uniqueness for linear systems. So generally, we don't talk about those a lot in engineering, even though it's good to still think about. But that would be why you haven't heard this much discussion about it before. It turns out the conditions are a lot more strict for nonlinear systems. So we're saying, okay, here is, so this existence and uniqueness of solutions. So here's what we have. We have this function, and, we have this differential equation, system of differential equations that are nonlinear, and we have this initial condition. And so the question is, so if I call this equation 1, when does 1 have a solution x mapping from some time interval to r to the n? So notice that we say a solution and the time interval could be small. So we just want to know, when is it true that there is any solution at all for any amount of time? So that's like not restricting to uniqueness and not restricting to solutions holding for a long time kind of loses a lot of power in what we want to achieve. But we can still say, like, okay, so here is the answer about that. So here is here's a statement. So if the function f of tx is continuous, on the set W contained in R cross R to the n, so on a set that includes the set of real numbers for t and R to the n for x. So this is talking about the right-hand side of this derivative being continuous. And your initial condition, so t0, x0, is contained in this set W, where f of tx is continuous. Then the equation 1 has a solution defined up to a certain time of t minus t0 less than or equal to c. So c is greater than 0, but it could be small. And this is a solution, so point here is not necessarily unique. So, in many ways, this is good in that it tells us that with just continuity of the right-hand side of the differential equation, then if our initial condition is in the set where f of tx is continuous, then we do get a solution. It's not necessarily unique, but we can get one defined for a certain amount of time, but maybe small. So clearly that's not really what we want. We want it to be unique, and we want it to go on and on instead of just going away, or instead of like making an unbounded state that cannot really go to a instead of making the state unbounded before later times, I guess. Any question on this so far? Okay, so then now we want to have something stronger than that will allow us to get better properties. So we see that continuity is helpful on the right-hand side, but it's not enough. So we can't just assume that we're going to have continuity and then be done. But note that we are talking about sufficient conditions, so it is necessary it's important to talk about sufficient versus necessary. So sufficient conditions would be, I make these, I state the following things. If these things hold, then my conclusion holds. But necessary would be like the opposite side, to say like, I need the following things to hold in order for like the following to hold. So the things that I just presented was sufficiency. So I said if the following properties hold, like there's continuity on the right hand side, then there is a solution that is defined for this time. But that doesn't mean that if that, like, for example, that solution is not unique, or that solution doesn't go on and on, or all these different things. Like, so we haven't disproved stuff through that statement. We have only said, if the following things hold, the following things hold. That's as much as I've said. I have not gone the opposite way and said, like, but if these didn't hold, now it's not true. So it's important to make those distinctions. So if the system has a solution, does not necessarily mean that all those properties had to hold. that we just said. So, now we wanted to have a unique solution. So, when does that equation have a unique solution? So, to answer this question, we're going to have to introduce something new. So this is a definition that I'm going to have to introduce, and it'll come back to this question about uniqueness in a minute. So here we're going to define the concept of a function being Lipschitz. So a Lipschitz function satisfies the Lipschitz properties Did anyone watch Rugrats when you were a kid?
That's what I've been thinking.
I know. Did you also, Enrique?
Yes.
Did you watch it in Portuguese?
In Portuguese.
Oh! Let W be contained in R cross R to the N. So this notation means like a subset or including the whole set. So as opposed to when we just use this one, it means it's like a strict subset. But this one means it could be a subset or up to and including the whole set. So let this be true, then F maps from W to R to the N be continuous in X and piecewise continuous in T. So far we have defined the set that we're going to map, that we're going to take the right hand side of the differential equation. So F has to be defined on this set W. We're going to require that F be piecewise or be continuous in X on this set and piecewise continuous in T on this set. Then F is Lipschitz in X on W if there exists an L such that, so L is a constant greater than 0, such that the norm of F of Tx minus F of Ty is less than or equal to L of X minus Y for all Tx contained in W. So I have to explain this better. It's very abstract. So here, let me explain this a bit. So the Lipschitz condition is defined like this. I guess in the proof of whoever determined existence and uniqueness like this, they must have used this in like this specific property in proving things. So this property actually comes up in other stuff too. So people have defined this property with relationship to norms as being something special. And then what this means is that, so if you take the norm, so you can see here how the idea of the equivalence of norms does become a little important when you start making these general statements about things being less than or equal to norms of other things. But that essentially you have this function, you take its value at all these different values of T and X in W. And so here, X and Y will just be different points in W. So I guess this should also be like Y or whatever is also similar to the X in this. But then if you do this, then this relationship has to hold. So it doesn't make a lot of sense until you start looking at a few examples, and even then it's hard to imagine what this means in 3D. But let's look at a few examples. So here's x, here's f of x, and so imagine that I have x squared. So here's the function x squared. So say that I take some region of it, so that even though I didn't take all of x squared, the question is, could I bound like this much of x squared with a line? And that's essentially the idea that's here for the one-dimensional systems, is that you can bound the function with a line. And you could see this by saying like, oh, okay, so what would this boil down to? So this would say that for every point in this region, so say this is the region from 0 to 1. So here I'm looking between 0 and I'm going up to 1. And I'm wondering like, oh, okay, so I would put my function. So this doesn't always, here Lipschitz continuity doesn't have to necessarily be only for differential equations. It can be for any function f. So that means that here I can look at this and say like, well, f of x is x squared. So I'm going to look at some point x squared minus, say there's a y squared, so some point, say this point is x, say this point is y, just some arbitrary points. And I ask whether or not this is less than or equal to the norm of x minus y times a constant L. And so we're dealing with scalars here, so we would probably think that it makes sense to consider absolute values. So something like x squared minus y squared is less than or equal to L of x minus y. And so we can see how that does look a lot like the idea of bounding something with a line. And then so of course you could go through and test this for like every point in the set, but then it would be equivalent to the idea of bounding here with a line. I think that's also similar to this idea of like y equals mx plus b kind of concept, where if you write that line in point slope form, it's something like y minus y0 is equal to m times x minus x0, if I remember correctly. So then I think this looks a lot like point slope form, where if you consider like this is the y, and then like you were to take one y and the other y, so essentially here y is the value of x squared at a certain value of x. So this is, so I guess I should call this differently. Maybe if you take it like z minus z0 is equal to this x bar minus x bar 0. So then if you compare this with that, you would say like this x squared is the value of x, or is the value of the function when x bar is x. I don't know if that's making sense. That I guess my points on here. So if I was to put this in terms of like x bar and z, so there's my coordinates on this plot. And then I would say like, okay, so 2 points on this plot are x and x squared, and then y and y squared. And then so I think that this looks a lot like plugging in these values here looks a lot like that. So I think that sort of helps to show this idea of bounding with a line. And then notice that you can bound with a line with the same slope everywhere in this interval. And so that's why we say there's this one L that holds for all of the points in this interval. So we say it's Lipschitz in X on this set W. But X squared itself, if you said, well, I'm going to look at all values. So let me just say my set W is all of R, and you looked at all of them. Then now you have to talk about locally Lipschitz, because this function x squared cannot be bounded everywhere with the same line because it goes on to infinity. Oh,
Bless you.
thank you. So then, since it's going to infinity, you can't bound it everywhere with the same line, but you could bound like little increments with the same line. Like I could bound this much with a line or this much, or I could bound this much with a line in terms of with like one line with the same slope everywhere. So we say that it's x squared is locally Lipschitz. Meaning that I could bound different increments of it with a line, essentially. Meaning that this relationship here holds for the same L in small intervals of each point that is in the total domain of R.
The same L?
Yeah. So if I, for example, on R, if I look at any subset of R, I could find a line with the same L everywhere in that subset that would be able to bound x squared in that subset with the same L. So it's locally Lipschitz because you can always break it down into pieces with the same line, but you could not use one L everywhere because then it would have to go off to infinity and this slope is like continuously increasing, so it's not possible to find one for everywhere.
And this is the meaning of piecewise continuous in T. You can break down the piece of T in small.
What it means about being continuous in T or continuous in X is so it's something like, so here's a continuous function. It has like a strict definition related to like epsilon delta. Something about like, oh, if you get within... oh no. If you, something, it's in the back of the textbook, I'd have to look, but it's something like, if every point you have like the function minus, like the function at one point minus the function at the other point is less than like epsilon, then like the difference between like x and y that give you those function values is less than a delta, or it's the opposite. There's some like strict epsilon delta definition of continuity. And then basically you can think of it like your function, you don't have holes and stuff.
Right.
And then if you want to do piecewise continuity, you can do stuff like, oh, it had like a gap here, and then, but it's continuous in pieces.
Okay.
Is that okay?
Mm-hmm.
So this is a property of this function, so it's going to depend what your function is. So it's allowing for you to define a function that's piecewise continuous in T, meaning that you would do something like, imagine you had like x squared plus T, for T is less than 0, and like x squared plus T squared for like T is greater than 0 or something.
Mm-hmm.
Now it's like somehow, maybe I don't know if this is even like that. This is probably still continuous. I don't know. But you can see like how, depending on the functions you're defining, it's not something we typically see in chemical engineering, to see wave functions like this. In chemical engineering, we typically don't see time dependence in any model.
There should be T greater than or equal to 0, I guess.
Yeah.
Or something like that.
Yeah. And this is probably a bad example anyway.
Mm-hmm.
Yeah.
Okay.
Because I think it's continuous. But that would be like the kind of idea, like if you were to be able to make a jump.
Mm-hmm.
Sometime. Yeah. Any question? Okay. So it'd be something about limits in X versus limits in, or like strict definitions have to hold, but you can see kind of the idea. Okay. So Lipschitz continuity is stronger than continuity. Oh, we only have 4 more minutes. So Lipschitz continuity is stronger than continuity. Because to be Lipschitz continuous, you have to already be continuous in X. So if something is Lipschitz continuous, then it's already continuous in X, and it has extra properties in addition. But it's not as strong as being continuously differentiable. But it is related to bounded derivatives in some sense, which you can see kind of, because if you were to take a 1D, say you do f of x minus f of y over x minus y. So since I is less than or equal to L. So this is what it looks like in one dimension. So you can see that if x and y get really close to each other, then that means that your derivative is upper bounded. So it's essentially saying something about nice behavior with respect to your derivatives is what's holding here in some way. But it's really defined by the Lipschitz continuity thing, but you can think of it by, if you want to try to analyze, like, what does it sort of tell me? It tells you these kinds of things. Well behaved. So, going back to our question, so when does equation 1 have a unique solution? X that maps from some t0 to t1. So now we're just handling uniqueness to r to the n. Note that this is just about uniqueness. We did not make any requirement that t1 has to be large. We just said, I want to find some solution that's unique. It can be over a small time interval, but I want to, when can I find one? That it must exist and be unique. But it doesn't necessarily yet, even though we're going there, have to hold for long periods of time. So this is if f is piecewise continuous in T, and Lipschitz in X, on T0, T1 cross some ball x0, which I'll define in a second. It's this norm ball, so it's not necessarily really a ball. We'll call it that. Then it's not necessarily a ball in the sense that it's not necessarily circular. But what does circular even mean in like n-dimensional space? So then one has a unique solution over some interval from t0 to t0 plus delta with delta greater than 0. But it may be small. And here's how we define this ball, this norm ball. It's defined as this, when I put this colon before the equals, that means this is a definition. So here it's a set of all x's in r to the n such that x minus x0 is less than or equal to r. So it's this norm ball of radius r, where you use some norm that's not necessarily the true norm. So you just define some norm, you take all the points where x minus x0 is less than or equal to r. We'll probably consider it like a p-norm. Let's consider that too. So here, Lipschitz continuity was very important in being able to guarantee uniqueness. And again, these are sufficient conditions. We did not prove that if you are not Lipschitz continuous, you do not have a unique solution. We haven't said that. What we've said is, if you're Lipschitz continuous, we can guarantee you this unique solution because someone's done a proof that shows like that has to follow if this Lipschitz condition is holding. But they didn't do the proof. Well, I don't know if anyone ever did a proof in the opposite direction, but I don't think so. I don't think you can say that, actually. I think there are probably counterexamples, but I'm not 100%. And so, yep, there we go.